after looking at the quantized form of light, multiple modes included, we've spent about 6 to 7 lectures on photon statistics. Photon statistics forms one mechanism of classifying the different kinds of light, quantum versus classical. Now we're going to spend 2 lectures on looking at photon correlations and detecting photons, with special emphasis on beam splitters and interferometers. We can also build quantum optical experiments using these techniques. So we're going to start a new module today on detecting photons. So this word photon, you've already seen what it means. It's an excitation of an electromagnetic field. And the word photon conjures the idea of a particle. And when we say that the photon is really a particle, it really means that it cannot be detected twice. Once you detect a photon, it's gone. You can't look at the same photon again. And the basic idea of how this works is, suppose you have a beam splitter, a 50-50 beam splitter, and a photon comes in, propagates. This beam splitter is half reflecting, half transmitting, and you have a single photon counting module here, T1, and a single photon counting module here, T2. Okay? So now what saying that the photon is a particle or a photon exists is tantamount, is equivalent to saying that if you see this detector clicking, you will never be able to see this detector click in the same run. So once this detector clicks, the photon is annihilated, it's gone. Likewise, if in a single run of a single photon entering this idealized beam splitter, this detector clicks, D1 will never click. So there is perfect anti-coincidence between D1 and D2. And if you would look at the correlation between D1 and D2, it's perfectly 180 degrees out of phase. So if this lights up, this remains dark. If this lights up, this remains dark. So perfect anti-correlation or anti-coincidence between D1 and D2. And that is what it means when we say that a photon exists. Now if I were to look at how do I get these single photons? How do I get them? How to get single photons? One technique is spontaneous down conversion. So if I have coherent light, we've seen these statistics of coherent light. The statistics follows a Poissonian distribution. And coherent light is the best light you can imagine in the classical world. Perfectly constant intensity. I cycle average T. This equals the long time average. This equals a constant I naught. That's what coherent light is. No change, and it has a single frequency as well. So if you look at the photon statistics in coherent light, it's still Poissonian. And if I were to take a snapshot of the beam and split this beam into small intervals, very small intervals, so that the likelihood of one small time bin being populated is some number, but there could only be 1 or 0 photon in any of these sections. The distribution of the occupancy of these time bins is Poissonian. It's not regular, it's Poissonian. If you have a number state, only then, in fact, if you had a single photon state, only then you would have a regular distribution of photons, or any number state, by the way. So this is sub-Poissonian, this is Poissonian. And one of the homework problems I gave, homework number 5, deals with looking at the statistics of squeezed light. And you will find out that squeezed light can also give you sub-Poissonian or super-Poissonian statistics. Okay, it's not explainable in the classical world. Now this is the most regular thing that you can have in the classical world. Now one can imagine that if I were to take a laser, single wavelength laser, monochromatic, and put some medium in between, and this medium is an attenuator, like a neutral density filter. You keep on adding material so that the intensity is reduced. And this is a coherent beam anyway. So one can imagine, one can naively think that eventually you'll get a single photon here. So there are trillions of photons coming in, but you block most of them. It might appear that at sufficient attenuation, the light intensity becomes so dim, that you get to the point of a single photon here in the separators at one time. But this only remains a naive assumption. If you have highly attenuated coherent light, it still does not satisfy the property of being more regular than a Poissonian distribution. It will still remain a Poissonian distribution. And the reason is that these photons sometimes they tend to lump together and come together in bunches. So they coalesce and come together in bunches. Whereas in this case, in this highly regular case, the photons are separate out. So this kind of light is called anti-bunched light. And this is bunched light. Chaotic light is also bunched. So even though we can attenuate a coherent beam, the beam at this point still remains coherent. Okay? It has very small average photon count number. We do know that for a coherent beam, alpha square, if you have a coherent beam kept alpha square, I do know, alpha mod square, I do know is equal to the average number of photons. Right? So you can get a very small number here. You can get a number smaller than 1, 0.1, 0.2, 0.03. But still it remains a coherent beam. And it does not show anti-bunched characteristics. So how do we get this anti-bunched characteristic, and what is a quantitative figure of merit of determining whether the light that you're seeing is anti-bunched or is quantum or is a number state or coherent or not? How do we get to these single photons? Okay, that's the purpose of the lecture today. So this was the motivation for today's lecture. Yes, please.
So is it then the fault is in our model, because we are assuming when we started the model for coherent light, right? We said that we're gonna takes a slice so thin in time, right, that only one photon can be present in that time, right? But what we're seeing in real life is that light comes in bunches, like you just described, right? So we didn't take that thing into account when we describe the model for coherent light, right? In real life, they are coming like हम यूजुअली तो हम बात कर रहे हैं ना कि एक ही हो सकता है उस स्लाइस में, बट रियल लाइफ के अंदर 2 भी आ रहे हैं, 3 भी आ रहे हैं, तो हमारा मॉडल को हम मॉडिफाई नहीं कर सकते?
कर सकते हैं, लेकिन whatever, even if you take a very small delta t, still the statistics will remain Poissonian. They cannot be smaller than the Poissonian. If you wait for long enough, this condition is going to be satisfied that the uncertainty, the distribution of these photon counts is still going to be proportional to the square root of the average number of counts in that interval. Okay, so we can try to come up with smaller and smaller intervals, yes, but still you will see that bunching behavior. Remember, some authors kind of think about, describe this observation in terms of the bosonic clustering of photons. That is, the photons are bosons and they tend to cluster together, right? They tend to bunch together. But I don't think that's a very good analogy. That's a really accurate description of what's going on here. So now my purpose is to give you an accurate description of what's going on. What are the mathematical tools that are needed to describe quantum light? Yes.
Just photons are bosons, right? So bosons like to stick together, right? तो उस सेंस में भी तो हम ये बात बोल सकते हैं।
हाँ, लेकिन तो यहाँ पे क्यों स्टिक टुगेदर कर रहे हैं? ये भी तो बोसॉन्स ही है ना? यहाँ पे क्यों स्टिक टुगेदर कर रहे हैं? So now what we would like to see is, in order to describe the bunching versus anti-bunching behavior of photons, what we really need to do, and we have a motivation that strongly attenuated beams, they do not give you number states. You cannot get to a single photon state using a strongly attenuated beam. We have to prove that. Now, in order to prove all of this mathematically, we really need to understand how the beam splitter works. So we need a quantum mechanical model of the beam splitter. So let's come up with a quantum mechanical model of the beam splitter. All quantum mechanics, when you describe quantum mechanics or quantum information, you talk about quantum states. We've seen that photons can be described by quantum states, squeeze states, and coherent states being examples. But then you also have transformation on those states. Those transformations are described by unitary operators. So really this beam splitter will be a unitary operator. So we have to come up with a model that describes the beam splitter in a quantum mechanical fashion. So let's come up with the quantum mechanical model of the beam splitter, right? Before we proceed with more sophisticated experiments. Okay? Now if you look at the beam splitter, the best way of describing the beam splitter is the following. Suppose I have a beam splitter which has two input ports and two output ports. So let's call this input port 1, the second input port 2. So photons will come through 1 or 2, the two input ports. Okay? And it has two output ports. Let's call one output port 3 and the other output port 4. Now when a photon strikes this intervening layer, this dielectric layer, it can either be transmitted or reflected. So this photon could be transmitted or reflected. This photon could be transmitted or reflected. Correct? And we assume that this beam splitter is symmetric in the sense that the probability of transmission on this line is the same as the probability of transmission on this line. The probability of reflection on this line is the same as the probability of reflection on this line. So this dielectric interface that constitutes the beam splitter is identical on both sides. That's our assumption. We can relax this assumption as well, but for the first introduction, this is a nice assumption. Okay? So now what we would like to kind of imagine is that if I have, so suppose the electric field that comes here is E1, electric field that comes in this output port is E2, here I get an output electric field E3, here I get E4. Eventually these are quantum mechanical operators and we would write those quantum mechanical operators in terms of lowering and raising operators. Okay, so now this output electric field E3, this can come from the transmission of E1 or the reflection of E2. So this can come from the transmission of E1. Now T is a complex number that gives you the probability amplitude of transmission plus R E2. So E3 can be made from some part of E1 and some part of E2. Likewise E4 can be made from some part of E1 and some part of E2. Correct? Now, energy has to be conserved. And remember that photons are not created or destroyed in the process. Okay? So this means that sum of the output electric fields, output intensities must be the same as the sum of the inputs. So E3 mod square plus E4 mod square must be equal to E1 mod square plus E2 mod square. Okay? And we have another constraint. The other constraint is that this is a 50-50 beamsplitter, which means that the magnitude of R and T must be equal to 1. Must be equal. Sorry. Now, if I impose this condition E3, because I know that the intensity is half C epsilon naught E squared. So E3 mod square plus E4 mod square equals E1 mod square plus E2 mod square. Now if I look at the right hand side over here, or I look at the left hand side over here, E3 mod square. E3 mod square, this thing is T mod square, E1 square, E1 mod square plus R mod square, E2 square plus T star R E1 star E2 plus T R star E1 E2 star. This is my E3 mod square. Alright. And my A4 mod square, this thing E4 mod square plus is going to be R mod square E1 mod square plus T mod square E2 mod square plus R square T E1 mod star E2 plus RT star E1 E2. Right? This must equal the right hand side. Now if I look at the coefficients of E1 mod square, they imply that R mod square plus T mod square must be 1, and R T star R plus R star T must be 0. Right? So at these two conditions, this must be equal, R mod square plus T mod square must be equal to 1, R star T plus R T star equals 0. Okay? Now these conditions. So this is energy conservation. Energy conservation gives some constraints on these complex numbers. Now if I look at these conditions, I can assume that both of these magnitudes are 1 over under root 2. Now I need to adjust the phases of R and T. So what generally happens, the phase between R and T generally depends upon the construction of this directivity. Generally it happens that when you have reflection, you get a 90 degrees phase shift. So one approach is to set the reflection, the T to be equal to 1 over under root 2 and R to be 1 over under root 2 EI pi by 2 to account for this 90 degree phase shift, which gives you I 1 over root 2. Okay? So these values of R and T satisfy these conditions. So what I've done is the reflection incurs, the optical field incurs a phase shift of 90 degrees. Generally, when light is reflected from a rare medium and it sees a dense medium and is reflected back, it sees a 90 degrees phase shift. This comes from the Fresnel coefficients that are coming from the boundary conditional due to the Maxwell equation. But it really depends upon on the construction of this beam splitter material. And we don't need to go into the details of this, yes.
हम ये नहीं कर रहे कि सारी जो लाइट है वो ट्रांसमिट ही हो रही है।
क्यों हमें क्यों जरूरत है? बीम स्प्लिटर है ये आगे आ जाए।
हाँ, लेकिन कोई रिफ्लेक्ट तो नहीं ना हो रही जो वापस जाए।
क्यों नहीं हो रही? ये रिफ्लेक्शन है ना। इसको हम रिफ्लेक्शन कहेंगे। ये लाइट है ये रिफ्लेक्शन है। Alright, so we have these values of R1 and R2. So what this means is that we can write E3, E4 in terms of E1, E2, right? 1 over and root 2, 1 iota, iota 1. Okay? So this matrix here is by the way a unitary matrix. It's proportional to e raised to minus I pi sigma x over 2. It's a unitary matrix. It's a 180 degree rotation about the sigma x body operator. So this connects the output electric fields with the input electric field, and this is the action of the beam splitter. The action of the beam splitter is a unitary operator. In fact, we can also invert this. We can find the inverse of this and express E1 and E2 in terms of E3 and E4. If I were to take the inverse of this matrix,
डैगर नहीं हो जाएगा?
हाँ डैगर हो जाएगा। Okay? So this is the action of a beam splitter. Either take this matrix or this matrix. The action of the beam splitter is now a unitary operator. And now we have a physical significance, by the way. Maybe the first time you're seeing this, that the unitarity is related to the conservation of energy. So unitarity in quantum mechanics is related to two things: conservation of energy and conservation of the von Neumann entropy. Right? So the entropy remains constant in this through unitary operator, and as well as the energy remains constant. Now what I want to kind of remind you is that the electric fields are represented by creation and annihilation operators. This is something that we learned when we were quantizing the electromagnetic fields. In fact, the relationship that we wrote at that point in time was E or T. This becomes I for the multiple modes E, K, S unit vector omega k, E omega k. This is the photon energy per photon summed over all k S A k S T E plus I k dot R plus A k S T dagger E minus I k dot R. Now we'll come back to this expression later. when we look at the photon atom interactions, but this is something that we've already derived. This electric field operator is related to the annihilation operator and the accretion operator. Okay, so what we could really do is we could replace this expression of electric fields, classical electric fields, by the ladder operators. So we could write A1, A2 equals 1 over root 2, 1 minus iota, 1, A3, A4. And likewise, we can take the dagger of this and write the corresponding expression for the creation operators. So now what we've been able to do is, so let me recast this in terms of A1 is 1 over root 2, A3 minus iota A4, and A2 equals 1 over root 2 minus iota A3 plus A4. Okay, so we have these expressions in front of us, and I put them in the box because I'm going to use them later. So I can also write this as 1 over root 2 iota A3 plus iota A4. Okay? Now what we could do is, let's look at the beamsplitter. Let's look at what the beamsplitter does. And let's do different kinds of experiments. First of all, let's look at an experiment which is simply equivalent to this experiment. Remember that in an experiment, in a real experiment, in the laboratory, we never measure electric fields. We measure intensities. So if you have a photo detector or a photodiode, we are measuring intensities. The intensities are being converted to currents. If we have a scenario in which we're looking at single photons, we have these avalanche photodetectors or single photon counting modules which are producing pulses for each photon. But we're never measuring the electric field. So we're measuring either photon counts or photocurrents, which correspond to the input intensities. So what we're really doing is that these detectors here are somehow looking at the number of photons. Okay? So we would like to do an experiment in which some light comes in into the beamsplitter and we have these two detectors, and we're counting the number of photons on the two detectors. No electric field measurement is. In interferometry, we're measuring electric fields. We're looking at the relative phases between electric fields. But here, we are shining light on the beamsplitter and just have two raw detectors at the two output ports. So this kind of experiment is looking at correlations between intensities, or correlation between the number, photo count numbers. So we're looking at intensity correlations. So this kind of experiment is called a Henry Brown twist experiment, HBT, which really looks at the correlations between intensities. Correlations between intensities. In the next lecture, we'll define the second order correlation function that precisely gives a number to this correlation, like an autocorrelation function. So we'll look at the correlation between intensities or photon counts. Alright, now suppose we have this beamsplitter here, two input ports, and a photon is in this port, port number 1. One photon is, suppose one photon is shown into the port. Now we want to see what is a photon. So one photon is shown into the port number 1. So let's write the quantum state as ket1 in this channel. Now I'm using a representation which is called the occupation number representation. There are different modes. This path, single frequency, single polarization, number of photons gives you a move. Single path, single frequency is one mode. And how many photons are in this mode? One. So this is mode number one. And how many photons do we have? One. So this kind of representation of quantum state is called an occupation number representation. How many photons are in this mode? One. And nothing comes in here. Nothing comes in the second mode. So one photon is shown into the beam splitter. But when nothing comes in it, actually it's vacuum coming in. So this quantum state in the occupation number representation is cat 0. So we are feeding the beam splitter with an input state cat 1 crossed with cat 0. Right? And in shorthand, you can write this as 1102. मोड नंबर 1 कि जो हॉरिजॉन्टल पाथ से आ रहा है फोटॉन, दो इनपुट पोर्ट्स है ना, ये है, ये मोड नंबर 1, ये मोड नंबर 2, ये एक पाथ है, ये दूसरा पाथ है, चैनल कह लो, पाथ कह लो, पोर्ट कह लो, ठीक है। तो पोर्ट नंबर 1 में एक फोटॉन और पोर्ट नंबर 2 में वैक्यूम है, कोई फोटॉन नहीं। Okay. So this is our input state to the beam splitter, and we want to find out how would the beam splitter act with its unitary operator on this input state to give an output state. Okay. So we want to find out how many photons. There are two output modes, 3 and 4. How many photons are in output mode 3, and how many of them in output mode 4? That's what we want to measure. So we really know that this thing can be written as, this is the creation of one photon in mode number 1 from vacuum. So this thing is A1 dagger. Correct? Now if I do also know that if I feed in vacuum into the beam splitter in both ports, nothing comes out because no photon is created. So this must give, under the action of the beam splitter, I do know this, right? This is energy conservation. No photon can be created. So now if I compare this with this, if I put an A1 dagger on both sides, remember I need to know upon which mode am I creating a photon. It's the first mode upon which I'm creating a photon. This must give A1 dagger O3. 4. Correct? Now if one dagger is given over there, A3 minus A4, correct?
Yes, sir.
Now it's so really nice, 1 over root 2. Now I'm going to do this extra step for you, but in later elaborations I will miss out on this. A3 acts on O0304. Okay? And A4 acts on, in fact it's a dagger here, right?
Yes, sir.
Plus here. Because I need to take the Hermitian conjugate of the top expression.
Yes.
Plus dagger, dagger. Okay? So A3 exclusively acts on its own Hilbert space. A4 exclusively acts on its own Hilbert space. So I'll get 1 over under root 2 plus iota this is my output quantum state emerging from the beam splitter.
स्किप करते हैं ना जो बीम स्प्लिटर और इवन डैगर है कम्यूट कर रहे हो बिकॉज
beam splitter or
इवन डैगर इवन मतलब जिस सेकंड इक्वेशन में
ये वाली,
हाँ इवन डैगर ऐसे कैसे आ गया बाहर?
क्योंकि हमने दोनों साइड्स पे A1 डायग्राम इंप्लीमेंट किए ना. So this goes to this. So this must go to this. Quantum mechanics is linear.
बाद में मल्टीप्लाई
अच्छा पहले बीम स्प्लिटर से गुजरा फिर इवन डैगर बनाया.
गुजरा ना गुजरा. So this is a mathematical expression. This is what the beam splitter does. It does nothing to vacuum. So this, if this is true, this must be true. So now look at this output state. What does this physically represent? This physically represents that, first of all, you've created a superposition. The beam splitter has created a superposition because the beam splitter is actually a Hadamard gate. It's created a superposition.
तो वो आयोटा आया हेडमार्ट में आयोटा नहीं आता
कोई बात नहीं यार, उसमें भी आसरा से Hadamard की उसमें आयोटा आती, doesn't matter.
तो बाद में
So this is a superposition. And the second thing is entangled.
yes sir
It's entangled between the two modes.
yes sir
So through a unitary operator, we have created an entangled state from a separable state. So if in this particular case, if the probability of detector, so if this is a pure quantum state, the probability of detector D1 clicking, now D1 clicks when there is one photon. Where is D1? इसको मैं D1 कह रहा हूँ. Let's call this D1, D1, right? Let's call this D2. The probability of detector D1 clicking is when there is a photon in channel number 1. And when that happens, there is no photon in channel number 4. So this probability is 1/2. It's 1/2. And this can be found in a number of ways. So it can be, if I make the projection operator 1, 0, 1,
वन राइट एंगल ठीक है
right?
ये ऐसे भी
This acts on this quantum state psi. And then I take the modular square of this. This gives me 1/2. So I can use projection operators to calculate this probability as well. But it's evident that this state is going to collapse. The probability of detector D1 clicking is 1/2. The probability of detector D2 clicking is 1/2. And when this clicks, this doesn't click. Because when this clicks, I have created, according to the postulates of quantum mechanics, a new state, which is this state, which doesn't have a photon in the adversely channeled. So this creates a superposition, and this really indicates a perfect anti-correlation between the two states. Another way of looking at this is, you have this quantum state psi, you create a density operator, rho, ket psi, graph psi, and then you find the probability of D1 is really the projection of you take this projection operator, multiply this with the density operator, and take the trace of this. You get 1/2.
सिंपली अगर आप 0 0 3 4 के साथ इनर प्रोडक्ट ले लें.
Alright, so another way of looking at it is you take this density operator, which is a 4x4 matrix, and take the partial trace with respect to one qubit. You'll get the maximally mixed state on the other qubit. Alright, so this is the Hanbury-Brown twist experiment, in which there is perfect anti-coincidence between the two photons, this channel and this channel. If photon clicks here, it doesn't click here. That's what it means that we have a photon. And the quantum mechanical description of the beam splitter kind of helps us understand this. Now let's move on to one other example that we kind of touched upon in the previous one of the previous lectures is a variation in which you input a photon onto both channels simultaneously. One photon coming into this mode, one photon coming into this mode. Okay? That was called the Hand-Mondel experiment. So let's look at the HOMI.
सर एक बात
हाँ
यहाँ पे जब हमने I get it कि वहाँ से हम कुछ भी नहीं भेज रहे but because photons वो हैं identical particles हैं तो हमें शुरू में ही state जो है वो ऐसा superposition नहीं लिखनी चाहिए
क्यों?
because मतलब let's say कुछ भी नहीं आ रहा मतलब vacuum state
लेकिन हमें पता है कि the one photon that we're shining in is in mode 1.
with certainty हमें ये बात
सर स्टार्ट यहाँ से नहीं करते हम कोई फोटोन है ही नहीं कि वो मोड 1 में भी जीरो है मोड 2 में भी जीरो है
देखो हमारी इनपुट स्टेट की है लेकिन ये इसके बराबर है तो हमें इफेक्ट देखना है ये एक मैथमेटिकल कॉन्स्ट्रक्ट का एक मैथमेटिकल प्रूफ है कि this gives this would give this. So let's look at the hand.
सर ये प्रोबेबिलिटी D1 में 0 कैसा है?
D1 में
हाँ ये जो केस के अंदर 0 है 0 क्रॉस क्रॉस 1
sorry 1
अगला वाला 0 होगा फिर
अगले वाला कुछ भी हो सकता है कुछ भी हो सकता है Alright, so now let's look at the Hand-Mondel experiment. The experiment that we just looked at is called the Hanbury-Brown twist experiment, in which one photon comes in and it doesn't split up, a superposition is created. But once you do a detection, that superposition collapses. Now, in this experiment, if I have one photon coming into this channel, one photon coming into this channel. So detected D1 here, and detected D2 here, and this is my 3, port 3, port 4. So what's my input state by the way? क्यों superposition होगी?
मतलब
एक दो फोटॉन्स हैं, दो फोटॉन है, एक फोटॉन नहीं है, दो फोटॉन है, एक इस मोड में, एक इस मोड में. सुपरपोजिशन तो नहीं होगी. इनपुट स्टेट की बात कर रहा हूँ.
1 1 1 2
स्टेट बोलो, इनपुट स्टेट बोलो.
मतलब 1 1 cat 1 1 नीचे 1 जी फिर 1 2 cat 1 2 और ये इसके साथ 1 by square root
क्यों?
मल्टीप्लाई करना
क्यों? This is our input state. That's it. One photon in mode 1, one photon in mode 8. So there's one photon here, and one photon here. That's it. This is our input state.
यहाँ पे हम ये assume कर रहे हैं ना कि we can distinguish them, right?
There are different modes, right? So these modes are distinguishable,
ठीक फिर ठीक
right? So now how do we find out the probability that detected D1 and D2 things? So if I use the same approach here, I start out with this. I want to build this, so I need to add a creation operator on both 1 and 2. So I have a creation operator on 1 and I have a creation operator on 2. So this gives me this. Correct? This must give me, after the beam, just this part, without the creation operators, of course gives me cat 0, cat 04, 0304. But now A1 dagger and A2 dagger also have to be inserted. A1 dagger and A2 dagger come out from over there.
Yes.
1/2. Now A1 dagger is A3 dagger plus iota A4 dagger plus iota A2 dagger is plus iota A3 dagger plus A4 dagger. Got it? So now let's complete this. Let's first break up or expand iota A3 dagger plus A3 dagger A4 dagger minus A4 dagger A3 dagger plus iota A4 dagger A4 dagger. All of this is acting on Ket03, Ket04. Correct? We just expanded the operation of the ladder operators. Now, if I do a successive one by one operation of these ladder operators, so 1/2, then we add a big bracket, iota A3 dagger. So A3 acting on this twice. Once I get Ket1, then I get Ket2, but within under root 2. So under root 2,
Yes, sir.
2 photons. And none in Ket4. Because A3 dagger squared only acts on Hilbert space of the third mode. Now this creates Ket1, Ket1. 1 photon in mode 1, 1 photon in mode 4. Minus. Now A4 dagger and A3 dagger usually commute because they act on different modes. Okay? Order doesn't matter. So this also gives me, correct? Plus iota under root 2 Ket0 all in all I will get iota over under root 2, 2 photons in channel 3, none in channel 4, or none in port 3, and 4 in. So what's going to happen is that all of the energy is either going to be deposited on D1 or all of that energy is going to be deposited on D2. Never would it happen that one photon out, so 2 are coming in, both of them are going either way. So the channel, these 2 channels, they destructively interfere in a sense. So this cannot be explained classically. This is only a purely quantum mechanical explanation for the Hand-Mandel effect, the Homey effect.
सही बात है कि जो लेजर ऑपरेटर्स लगा रहे हैं 0 फोटॉन का 2 फोटॉन्स बनते हैं फिजिकली किस तरह होता है एक्सपेरिमेंटली क्या चीज़ें फिजिक्स में
तो ये देखो photons are being, number of photons is being conserved in this experiment. So it's a totally linear process. There is no non-linear process here. No energy is being created. None of them is being diverted. So there are cases in which you have non-linear effects. So 1 photon comes in and 2 go out. That's a non-linear process. Squeeze states are generated, for example, through non-linear processes. But here we have a totally linear process. So there are 4 possibilities in this case. If I look at the world of outputs, one possibility is this. The other possibility is this. And the third possibility is this. In fact, there are three distinguishable outcomes. Remember that the two photons are indistinguishable. Only then would it make sense. So, if you really want to see this impact in the body, the two photons must have the same energy, they must come in at the same time. So, they must be indistinguishable in that sense. Now, these are the three possibilities. But the probability of this event happening is 0. And there are two ways in which this event can happen. The two ways is that this photon is reflected and this photon is transmitted. Sorry, this photon is reflected and this photon is, both of the photons are reflected. Second possibility is both of the photons are transmitted. So there are two ways in which this can happen. But both of those ways, they destructively interfere with one another. So this is also consistent with Feynman's sum of histories approach, in which some event can happen through multiple ways. There is an action associated with each trajectory, and those actions are such that those trajectories destructively interfere. So you can give this experiment a Feynman's sum of histories interpretation as well. So this event never happens, but this event happens, both of these events happen with equal probability. Okay, now how else in the world without quantum mechanics will we be able to describe this? So we need a quantum mechanical model of the beamsplitter, and that quantum mechanical model helps us describe these observations. Now my original question with which I started the motivation is that if I have coherent light coming in, even though if it's attenuated, what do I observe at the output? Even if it's attenuated, do I get the same effect as I do for the Hahn-Green twist experiment? That is one photon coming in and either of these detectors is going to click. It turns out that coherent light, even if it is strongly attenuated, is not going to give this particulate quintessential nature of the photon. It's not a photon, it's just light. It's just this electromagnetic radiation. It's not a photon in the particular sense of the word. You cannot see the graininess of the photons with coherent light. Okay? But coherent light is quantum mechanical because it has a quantum uncertainty and so on. But it will not elucidate, manifest, evoke the particulate nature of a photon. And that's what we're going to do now. So we're going to shine coherent light onto a beamsplitter. The coherent light is described by the quantum mechanical state ket alpha and the beamsplitter by the unitary operator that we discussed, right? So let's look at the coherent light input into a beamsplitter. So once again, I have my beamsplitter, and this time I just shine this with ket alpha, okay? And once again, I have two detectors, D1 and D2. Now, what is my input state? What's my input state?
सर आगे D1 और D2 अभी सिंगल फोटन काउंट
बिल्कुल single photon counters. Suppose this is highly attenuated, so there is still single photon counters. Okay, let me assume a coherent state which is highly attenuated. But even if it's not highly attenuated, I can still assume that these are regular photodiodes.
सर ये हैंगबेरी ब्राउन ट्विस्ट में और हैंग ऑन मेडल में जो अनसर्टेनिटी रिलेशनशिप है कि हमें पता चल गया भाई अगर लेट्स से इधर आ रहा है फोटोन तो उसका अनसर्टेनिटी रिलेशनशिप किस चीज़ के साथ है, पाथ के साथ?
बिल्कुल पाथ और मोमेंटम,
पाथ और मोमेंटम, और उसके अंदर भी सेम होगा?
उसके अंदर भी सेम है. उसके अंदर you have two outputs. If you get 2-0 or 0-2, you can say that there are two photons and both of those photons are in both of those channels. Okay? So now coherent. So what's the input state over here? Ali alpha. So this is the displacement operator,
Yes, sir.
right? This must give after the beam splitter D1 alpha, right? Now D1 alpha, this thing we do know is E is what alpha A1 dagger
Yes, sir.
minus alpha star A1. Now if I use the Baker Campbell Hausdorff formula here, BCH formula here, I know that A1 dagger does not commute with A1. I know that. But the commutator is a scalar. So I can break up these two operators with some phase factor. Right?
Yes,
Well, this is a scalar. So I can write this as E alpha A1 dagger E minus alpha star A1. Alright? Using the Baker Campbell Hausdorff formula. BCH formula. So, but this is a global phase intermediate integral, so I don't need to consider it too much. I don't need to consider it at all. So the output state, which is this state, I'm going to focus on the output state. At output, right? This is E alpha. Now A1 dagger is gain over there. It's in the exponent 1 over root 2. A3 dagger minus plus iota A4 dagger E minus alpha star A1 1 over 2 A3 minus iota A4. Right. So this acts on cat 03, cat 04. This is my output state. Now what I do know, so I know a few things. First of all, I know that A3 dagger and A4 dagger commute, right? Because they act on different input states. I also know that this thing, this is the dagger of this, and hence they do not commute. This overall operator is simply the dagger of this, hence they do not commute, but their commutator is a scalar. Right? So another global phase comes in. So both of these properties let me break this up and expand this product of exponents with sum in the exponents as simply the product of different exponents without a sum in the exponent. So I can write this as E alpha over under root 2 A3 dagger minus alpha star under root 2 A3, right? E iota alpha over under root 2 A4 dagger plus iota alpha star over under root 2 A4. Okay? So this operator is a displacement operator acting on ket 03, and this is a displacement operator acting on ket 04.
So बराबर एंटिटी को फैक्टर हुआ है.
कोई बात नहीं, नया कॉम्प्लेक्स नंबर आ जाए. जनरल फॉर्म ये है, कोई कॉम्प्लेक्स नंबर. This is a complex number, so this really gives me
ठीक है.
alpha 1 under root 2
बराबर एंटिटी को भी कैट आ जाएगा.
and this gives me iota alpha.
Yes.
Both of these are coherent states. So at the output, I get a coherent state here, and I get a coherent state here. So what is the average? What is the probability that I detect photons here, or what is the average number of photons detected on this channel? So if I shine with coherent light, the average number of photons is the modulus square of this, which is alpha mod square over 2. And the average number of photons detected over here is going to be modulus square of this. Because what will happen, look at this expression. The average number of photons detected due to this state is given by the modulus square of this number. This is the average number of photons detected. So the average number of photons that are, of course this is not a single, it's not a number state or a Fock state. They are in coherent state, so many photons are coming in. Per unit time, the photon counts can be small, it could be less than 1 even. But whatever the counts of photons are coming in, half of them will go here and half of them will go here. Correct? So even if there are 0.6 photons on average in a certain amount of time here, which is much less than 1, supposedly even better than a single photon state. Very few photons here, but it's a coherent state. Half of that, those photons are going to come here, and half of them are going to go here. You will never get perfect anti-coincidence. So even if you strongly attenuate a coherent beam, you do not get this anti-coincidence between these photon counts. So it does not reveal the photon nature. It does not reveal the quintessential particular nature of a photon, this experiment. Okay, any questions? ठीक है, तो coherent state को भी हमने फैन के देख लिया. कुछ हाँ, perfect correlation होगा. If this intensity goes up, both of these intensities will go up by half the amount. If this intensity comes down, both of these intensities will come down. And when we define in the next step the second order correlation function, this number will be greater than 1 or equal to 1. Equal to 1 for a coherent state. And it's going to be less than 1 for quantum states. So we're going to define this correlation function in the next lecture. अब मैं क्या इसी की एक corollary कराना चाहता हूँ. हाँ. Okay, so one question that I have, if I define an operator, a measurement operator, which is given by this projection operator minus So this tells us the relative difference between the counts on the two channels. For a single photon state, we know that this is either plus 1 or minus 1. Right? So perfect. So this will, if this is 1, this is 0. This is 0, this is 1. But for a coherent state, if I were to find out the expected value of this operator for this output state, what would it be? 0. What will be the uncertainty? The uncertainty will not be 0. The uncertainty in this operator will not be 0 because the coherent state has a non-zero phase uncertainty. The coherent state has a non-zero amplitude noise. It has a quantum noise, the short noise. So but this number will be at the short noise limit. So at the limit of the short noise. This kind of scheme is also called balanced homodyne detection. Now what we would like to do is we would like to kind of do a more advanced experiment in which we put two beamsplitters and try to build an interferometer. So let's build a quantum interferometer with a single photon. By the way, a very interesting observation is in this experiment, this is the, if I have coherent state here and I have a squeezed vacuum state here, I get a squeezed coherent state. The question is, how do I create a squeezed vacuum state? We'll come to that point. We need a non-linear process to create squeezing. Because the squeezing operator has biphoton operators. We need a non-linear process to create two photons out of nothing. And that's what a squeezed state does. It creates two photons out of nothing because in the exponent, if you recall, it has an A dagger square. So we need a non-linear crystal to achieve that. But this mechanism, this formula is very important if you want to understand how to create squeezed states. So if in this port squeezed vacuum comes in, this is a coherent state, and this coherent state overwhelms this, then this will be a squeezed coherent state. Okay. Now let's try to build a quantum interferometer from two beam splitters. इंटरफेरोमीटर का मतलब क्या है? इंटरफेरोमीटर का मतलब ये है कि उसके अंदर जो मुख्तलिफ पाथ्स हैं, जो एम्पलीट्यूड हैं, उनके फेज की वजह से आपस में इंटरफेरेंस हो सकती है और फेज की वजह से वो सप्रेस हो सकते हैं, कुछ पाथ्स हाईलाइट हो सकते हैं. So to give an example of a quantum interferometer in photonic quantum optics. So let me have a beamsplitter here. Two beamsplitters, B1 and B2, right? And there are two mirrors, M1 and M2. So what the mirrors do is they just change the path of light, and they might apply a 90-degree phase shift on each of these paths. So suppose a single photon is fed into the system, vacuum in here. So this beam splitter, after this beam splitter here, we know that we've created a superposition state given by this. So after the first beam splitter, we have created 1 over under root 2, 0, 3, plus iota 1. Alright, this is after the first beam splitter. Now so what the mirror N2 does, this is one path, right? Let's call this 3, is called 4. So if a photon comes in here, it gives you a 90 degrees phase shift. So this is after this mirror, M2. This also, this M1 gives a 90 degrees phase shift here. So this is after the two mirrors. But since the 90 degree phase shift is common to both paths, we can ignore this as a global phase.
सर M2 ने सिर्फ सेकंड वाली स्टेट के ऊपर क्यों फेज दिया?
क्योंकि फोटोन इस पाथ जो पार्ट 3 पे फोटोन आ रहा है बिल्फर्ड से, उसी पे देखे ना फेज शिफ्ट, इस पे तो नहीं ना दे सकता।
तो हमें क्या पता कि पाथ अच्छा ठीक है?
ये ना लीनियरिटी देखनी है ना कि ये एक जी पेट है दरअसल, जो कि कैट 0 पे एक्ट नहीं होता, कैट 1 पे एक्ट होता है। ठीक है, सिर्फ पाथ दिखे, दिस मिरर कैन ओनली impose a phase shift onto this path. It can't impose a phase shift onto this path. It's not there. But the phase shift is immaterial because it's a global phase, so I can just might as well drop this phase shift. It's global. Now what happens is, now this quantum state reaches the second beam splitter over here. At this point, this beam splitter also has two input channels. So this is 3 and 4 for this. So let me relabel this path as 2 and let me relabel this path as 1. Or I can keep 3 and 4 and give this 5 and 6. The output ports 5 and 6, but then I will get slightly confused in my head. So I'm going to relabel this path as 2 and relabel this path as 1. Because these are the inputs for this beam splitter. But 3 और 4 भी रख सकते, लेकिन फिर मुझे को 5 और 6 कहना पड़ेगा, फिर मुझे ध्यान रखना पड़ेगा। So I just do a relabeling here. So this becomes 1 over root 2, 0 2 plus iota 1 2 0 1. Alright? So I've replaced 3 by 2 and this path 4 by 1. ठीक है, just 3 को मैंने 2 कह दिया और 4 को 1 कह दिया. Now I need to apply the second beam splitter. And I do have the relationships. This is I can write this as, I can switch the order here. Okay, I can switch the order, it doesn't matter. This is A1 dagger 0 0, right? And this is iota A2 dagger. Correct? अब क्या होगा? This is after the second beam splitter. Now I can use these expressions over here for A1 dagger and A2 dagger.
सब switch कैसे कर सकते हैं? तो जो iota है ना, वो है basically
ना करो switch यार, आप इसको 2 और इसको 3 और 4 ही कहते हैं, तो इसको 5 और 6 कहते हैं.
वो तो relabel है जो आपने
तरतीब switch की है. क्यों नहीं कर सकते? This is Hilbert space number 2, this is Hilbert space number 1. I'm just changing the order. कर तो सकते हैं.
one
तो A2 डैगर नहीं होना चाहिए टाइम पे, बिल्कुल आपकी वाली लाइन में. नहीं इससे पहले सर.
इधर?
नहीं सर, उसी में जो फर्स्ट टाइम है इधर आपने A1 डैगर लिखा जब.
ये?
हाँ ठीक है. यस
इसको मैंने लिख दिया ना?
सर ठीक है.
ठीक है, और इसको मैंने ठीक है. So this is my output. Now if I put in the expressions of So this really is 1 over root 2 A1 dagger. What is A1 dagger? It's over there. 1 over root 2 A3 dagger plus iota A4 dagger. This part is simply K03, K04, correct? This part. Plus iota A2 dagger. A2 dagger is 1 over root 2 plus iota A3 dagger. Plus A4 dagger. So now let's compute all of this. If I were to compute all of this, so coherent करके देख लेते हैं जबरा है इसमें एनालॉजी का इस्तेमाल कर लेते हैं 1/2 A3 dagger acting on this gives me 1/0 plus iota 0/1, right? Iota minus 1/0 plus iota 0/1. Now look at these terms, this term and this term. For convenience, let me put 3 and 4 again. These terms cancel out, destructively interfere. And I'm left with iota, which really means that if I have two detectors here, and this is an equal superposition of two paths in between, but only one of the detectors is going to click. This is interferometry. That interferometry, because there's a bright fringe here or a dark fringe here. Bright port, dark port. And if I were to change this experiment in a fashion, now all of this is explainable through quantum optical measurements. If I were to put here a medium, say phi, which produces a phase shift. So what this does is that it produces, whenever there is a photon in this path, it gives you phase shift Ei phi. I would like you to do this as a homework. Then the probability that this detector is going to be cosine square phi by 2, and this probability is going to be sine square phi by 2. And if I were to compute that polarization operator, O operator expectation value, that would be equal to alpha mod square cosine theta, cosine phi. This is probably a homework problem. So this is quantum interferometry. Now this experiment, this example, there is also phase noise. And I will give you a homework problem to calculate that phase noise. The answer is in the phase. This kind of interferometry is really important in experiments. For example, in the detection of gravitational waves. And the efficiency of this process will be enhanced, the phase noise will be reduced if instead of single photon we use squeeze states. Alright, so this is quantum interferometry. This is an example of quantum interferometry. In the next lecture, what we're going to do is we're going to discuss this second order correlation function and see how this can help us distinguish between bunched and anti-bunched light. Today we've looked at the operation of beam splitters, interferometers, and how those beam splitters can be assembled together to make larger quantum optical experiments with quantum states. Okay? Yeah. Perfect absorber. But we don't have the luxury of opening up the box and finding out whether this box exists, this blob exists. If in some experiment, one want to ask the question, is one of the paths obstructed? If D4 clicks again, it's inconclusive whether the object exists or not. But if D3 starts to click in one experiment, you keep on shining photons one after the other. Sometimes D3 is going to click. When D3 clicks, can you be certain that one of the paths is blocked? So by observing a photon here, you have detected the presence of an object, but the photon has not interacted with this object. Because the photon had interacted with this object, then it will have been absorbed here and there. Right? So, but it does sometimes happen that the photon is absorbed here. And then D3 will never click. But in that case, D4 will not click either. So if you have set up this interferometer such that it's perfectly balanced, and you have the question whether an object exists or not, and a D3 clicks, you can be certain that this object is there. So the detection on D3 necessitates the presence of an object in one of the arms. So this experiment helps to detect objects without having photons interact with them. This is called an interaction-free measurement. This experiment is really, really important, interaction-free measurement. So then if this were a bomb is triggered by a photon, but now you can tell that the bomb exists without ever having to explode it. So this is a really interesting twist to a quantum mechanical process.
Entanglement की वजह से ही होता है.
Entanglement नहीं actually non-locality है.
ये uncertainty principle से नहीं होगा.
सारा कुछ ये सारा related है, but the best explanation for this is non-locality. You have an experiment outcome somewhere, but the object or the experiment is happening elsewhere. चलिए इंशाल्लाह.